Hello everyone, welcome to Edicil. In this video, we are going to discuss about randomized hashing, which is a part of randomized algorithm. Those who are new, kindly watch the previous video, which is related to randomized quick short. There we discussed about certain part of randomization. And before going to the content here, I must tell you, like I have followed the Tardos books PPT there in Princeton University, as well as I'll keep the content of this one through the description. You just find it out, and let us start. So as per the book, they have actually focused on the dictionary data type, where they have focused on certain functions which is named as create function, which is in book they said as make dictionary. So they're initializing the S is a set basically, which is a subset of universal set. Dictionary, before that we should know what is dictionary. Certain interfaces we should discuss after that one. So dictionary is a given universe u possible elements maintain a subset where inserting, deleting and searching here is renamed or named as lookup. Okay, so lookup in the book it is written whether at position of u whether the element is there or not. Whatever the element, it will be definitely shown. If what you are going to find it is not there, so in this place what is there, it will be displayed as per the dictionary. As you have shown already, you have seen many type of applications. It's a kind of data type. As per the book, they have just created it. So then we'll go through the hashing first. Next, insert means definitely we are adding it. Deleting, we're deleting any element present in that position. We have to delete that from the subset S from the universe. Universe means you can think all the elements are present there. Just S is just a subset of the universe. Okay. Next, challenges. What are the challenges that we should have to take care of? Is like universe U can be extremely large, so defining an array of size S is infeasible. Though I told you like it keeps all the elements. Whenever we keeping all these elements into an array, so it definitely it's large enough. So it's infeasible for us for the timing. Like how do we just keep all the elements within a certain array? That is what a challenge is. Okay. So we can be resolving those challenges using the hashing or hash. Applications are like file systems, databases, Google Compiler. These are certain applications we can do. In general, I can tell you like what is hashing or why hashing is used or why hash table is getting used. Like as you have known, like have idea related to hash map, hash set, hash table, certain hash related things that hash basically we are using in real life. I must tell you, like when you are just watching or just reading a book, that there is a content page you have. So based on the content page where the page number is mentioned as well as the content is mentioned, the title with the page number as well as certain serial numbers are mentioned. So whenever you are reading a book, the first you can go to the content. If you want to search anything, so it will definitely take less time as compared to the books you are just reading, just switching all the pages there, you just finding the content. Better you can search to the content page. There whenever you got the information, so that what you have to do, like you have to find the title with the page directly, you search there. So indirectly it's a combination of linked list we are using there. And the main target of using hash table or hash type of data structure is that we can insert, even if we can delete, we can search that using big of 1 as our complexity should be, without taking big of n. Suppose you are searching, okay, it's not be taking big of n, because if you are containing or you have certain contents clear in the book, you just find the title with the page number, you directly switch to that page number. This is what a big of 1. So this is a use of hashing basically we are using. So how do we hash, like how do we sort the all the elements within this hash? This is our challenge. whereas universe means the all the elements that we need to switch or we need to reduce to a particular array. That is what our target. The array which contains all the universal elements or subset S is hashing, we can say. Clear? So we are reducing that universe or to set to slots, a number of buckets as per the book. We can say the reduction is getting takes place. Like you can say if there is a set or you can say universe which are trying to reduce towards a hash table which is you can say named as V, suppose this is your hash table. So what you are doing, this is your hash function which helps you to keep the value stored in a particular position which is named as h, also small h. So let us go in deeper, like what is hashing. Like as I told you, just a brief idea about what is hash. Next you can easily understand the hash function. Hash function is like the universe is getting reduced, as I told you, like from the universe is getting reduced to these many number of buckets or slots available within a hash. I'm just saying number of slots available within a hash table. Clear? So this is what we can say is a number of slots available within a hash table. Hashing is like we are going to create an array. Clear? Of you can say suppose the array name is A. You can do that one. And the length is N. This represents the number of slots available within that. When we process the element U, that should be said to be the position is within that array. We are using a function which will help us to reduce that one. Suppose you can say I have I must tell you, like universal is, you just think there is a certain keys are there which is named as also m number of slots or m number of keys. I'm just writing that one, m number of keys or elements, n is number of slots within the hash, okay, and h, small h is hash function. These are certain of the naming conventions we should know. Next, a is just an array for us, or you can say it's a hash table for us. So the main reason is whenever you are doing hash in general, so if I'm saying the slots are 4, so it is 0, 1, 2, 3. Like the slots will be started from 0 towards n minus 1. That's why it is written in this way. Suppose I'm saying the hash will have 4 slots that could be represented in 0, 1, 2, 3 format. Clear? So if you want to suppose be taking care of, like you can think of 4 is a key that you want to, there is a key or element you want to insert this one, and where to insert this, you can think of for a hash function. Suppose this hash function will be like key modulus the slots or n. In this way, what you can say, if key is 4 modulo 4, so definitely the answer is 0. So the findings are, so sometimes you are facing issue, so I must tell you the trick. If this side, okay, is equivalent to this side, so definitely you can expect 0. If this side is greater than this side, so this value will be displayed. Clear? Means suppose you are be having like 3 as your answer. Here 3, here is 4. If 3 is less than this, so finding modulus, it will be 3 directly. So if it is greater than, so you have to divide this, and the remainder we have to use. Suppose here is 5, so you have to divide it with 1, and definitely you can say the remainder is 1, so you can write it 1. So less than or equal to, it is very easy to find out, and for greater than, you have to find the remainder of it. So as we found, so 4 is getting inserted in the zeroth position as per our hash function. Hash function, it depends. Whenever you are creating hash functions, without hash functions we cannot insert any data to the hashing. So in a hash table. So what we have to do is, when we are inserting that one, this is called as hashing. Okay. So you can be expecting, suppose 8, next key is 8. Whenever we are inserting next key 8 modulo 4, definitely we can say it is 0. So when 8 is coming here, there will be a chance of collision. So to avoid that one, we have probing. Probing means if it is available, so it will be +1. Either you can say linear probing, quadratic probing. There are many type of probing. Okay. So for linear probing, I can add +1 to it and I can store. But it will be having like, if the slots are 4, and if I am interested to keep only 4 keys inside it, there will be not any issue. If keys are more, if keys are more than the slot, keys means I can say m is greater than n, there will be a problem. What, like if 5 elements to be inserted into 4 number of slots, definitely one is there which will be going to collide with other, so that has to be avoided. So that is what we need, a universal hashing through which we can store the value, but our main target is there should not be there might be a less collision. Okay, this is what our target, what our aim to be achieved. So collision will be like if h of u and h of v means the locations for both the different items, like u and v both are not same. Clear, like as 4 and 8 are not equal. So for this case, we are having the same position to them. So their collision could be expected. A collision could be expected after this type of random selections, like theta of root over of n. N means the number of slots available. So which is birthday paradox. It's said to be birthday paradox, like you are getting this one. And also separate chaining concepts that we have to introduce. If number of slots are more, so what do I do? Like I can do as per the chaining. Chaining is a usefulness of our linked list. So here I can use this 8, and I put a backslash that I stopped here. This is what it says. Okay, so I can do this one. This called as chaining. So through chaining also we can do, but chaining is having a problem also. We have to follow the load factor, which is named as alpha. So it depends on that one. So this is also the example. You can check it here. Through that we can do, but the collision is not getting avoided. So our main target is whatever the h we are going to decide, that should be you can say such effective one which will uh, build less collision could be expected. So here the idea is also written, like how we are doing the hashing, how we are improving the hashing basically. So the idea, such function like maps m elements uniformly at random with n hash slots. Okay. Running time depends on the length of the chains. Definitely, because we have the length of the chains, because it's a linked list, by the way. Average length, whenever we are finding the average length, which is the load factor, is getting introduced here. That should be m divided by n, means a number of elements. If it is more than the number of slots available, so definitely we will be focusing on the load factor. So choose n which is nearly equivalent to suppose m. So definitely we can say or everything will be in its position. If it is more, so there will be a problem. For this case, we will definitely get or insert, lookup, delete, definitely will get as big of one. Clear? So for the challenge, basically what we are having, like h, we have to create a generate a h, which is hash function. I'm just writing this h as hash function, which should achieve big of 1 per operation. Operations are like insert, lookup. Lookup means search. Okay, delete. These three operations. Whenever we are operating, it should give us big of 1. Approach is use a randomization for choice of h. We will do randomization procedure through which we can expect the we can at least achieve big of 1. That's why we are introducing randomization here. So here it advisory known as here that randomization, it is written as advisory known as the randomized algorithm you are using, but doesn't know random choice that algorithm makes. Okay, whether the random choice what you have done, whether it is so much efficient or not, that we are going to discuss here. Clear? So universal hashing, which is named by the Carter and Wegman in 90s 80s. Okay, so a universal family of hash function, which is in general we can represented, this one is h, like it's a universal family of hash function, is a set of function which is h, like as I told you there, mapping a universe u to a set 0 to n, like n minus 1. You can say either n number of slots, or you can start it from 0 to n minus 1, such that for each pair, as we have already said, like if both are not equal but they are keeping with a one slot, so the probability should be 1 by n. So we are considering these two elements. That's why you can say it is 2 universal. As per the content I have seen, it is also considered as 2 universal once you are focusing on two different items. If you are focusing on suppose k number of items where x and y are to be introduced, in that case it should be like for k universal, it should be following this concept, like here x and y you need to introduce in between. You can search, definitely you'll get it, but in the book k universal is not getting mentioned. But just for your confirmation, I'm just saying you, like k means the k number of items are getting multiplied here. Here also it is getting multiplied, and it should follow this condition, means 1 by n to the power k, or else you can say 1 by n whole to the power k, because 1 to the power k and here n to the power k, 1 to the power k is 1, 1 to the power anything is 1, that you know, and n to the power k. So this is for k universal I'm just talking about, but here we are focusing on the 2 universal. By the way, why we say it's 2 universal? Because we are just focusing two different items, we'll be focusing for one slot. That is what we should have to focus with the probability. PR represents the probability of it. So I'm just writing here the PR is probability. Clear? So it's a probability factor. Small h is just, you can say, our you know small h is hash function, and h is a set of universal family hash function, where our target should be, it should be 1 by n, less than or equivalent to 1 by n, then we can say it's a part of universal family, otherwise we cannot accept that one. But can select a random h efficiently and can compute h of u efficiently. So we have to check the probability first, then we can go for the efficient checking of this one. As for the example, it is there, like if a b c d, like there are 6 different elements, or you can say these 6 m are there, but n is 2, means slots available are 2. So in this case, what we have to do, probability of getting ha and hb is 1 by 2, like you can say is your a and b, which is having the same one, You can expect these are max to max is 1 by 2, but in this case it is 1, so what is not a part of universal, at least it should be equivalent to 1 by 2, or it should be less than this, then we can say it's universal. So here it follows the term or condition, that's why it is a part of universal. In this case you can say h of a and h of b, here it's equivalent. Clear? Like this you can check uh, other conditions too, which is following this condition, so definitely we can say it's a universal. I hope it is clearly understood to you. Next, this analysis will definitely it will play an important role. So what the proposition it says, let H be universal family of hash functions mapping a universe U with a set, like the set represents here is the number of slots available is n, and let h belongs to h, when small h is a hash function, a single hash function, and h is a universal family one. So choose uniformly at a random from h, where s is a subset of u, which is universal one. So which at most n number of slots within that, means m is equivalent to n. This is what we are going to discuss next. Whether it exactly says this u is not belong to s, means whatever the u we are trying to find out, the u is not present there, then the expected number of items of s that collide u at most 1, means whenever it is not there, let u doesn't belongs to s, means u is not there in a subset s. So what the expected number means, if you are finding this one, like the collide in future, if you are colliding, so at most means at less than 0 or less than 1 or equivalent to 1, not more than 1 we expect. Clear? As per the probability factor, as we have already discussed. So as per the proof, if s belongs to, means small s belongs to capital S, small s is like u, because it's a kind of element. So as for the definition of random variable, xs is 1. Xs is a uh, the capital X of s, means we are just randomly picking one element or randomly picking one variable. It is 1 if h of s and h of u is at same position. Otherwise, it is said to be 0. Let x be a random variable counting total number of collisions with u. Any random variable we are picking, and as it is already being captured by you, we just want to verify. Clear? So for that we are saying this is one expectation of x that we are to check when we are doing the expectations. So expectations clearly says, uh, it may not be written like this as per the book, so it was omitted there. You can keep or you can omit, but as per the book it is not there, but here the PDF or a PPT PDF you can say it's there, but I should go for the book one. Okay, so here expectation value when we are finding, so expectations here in place of x you can say up to S, the number of elements present within the S, we are trying to find out one by one, and we have to find out the expectations. When we do the expectations, so this one will be going outside and expectations will be inside, because expectations directly for the sigma we cannot find it out. So when we just keeping aside, and here we say the expectations recently we said is 1 by n, as per the you know recently we discussed, whenever we say expectations of this element will be 1 by n, means it will capture at least one position out of n number of slots. This what it says, a ratio we are maintaining. So the probability, when it comes to the probability one, so 0 1 random variable, just check with the linear expectations. Linear expectations means we will keep the sigma aside and we will keep the expectations of this one. So expectations means we will expect this element, whether it will be collide in future or not. So here the probability we will be finding out, it should be less than this one, and this result we will be getting using the universal condition. This universal condition will helpful for us to find out, because if you're finding one element, so definitely it will be capture one of the slot among all the number of slots available. So this answer means up to this we are finding, up to S. So the number of elements present there is called as the sigma factor we are using, or you can say whenever we are adding it, so indirectly we can say it's a number of elements. So this is less than 1 as per the proof we found. So this analysis is very much important for us to understand, like how do we expect, uh, you know if the element is not there. So by the way, we are talking about the element is not there. If the element is existing, in that case we can expect 1 plus m minus 1, because 1 is already there, and out of that other, you can say, slots are available if u belongs to S. So in this case what we have to do, like everything will be same as it is. So we have to just add one more thing, because it's there existing. So we can say for m equal to n, we can say two condition we can expect, because approximately we can say it is 1 and 1 plus 1 is 2. We can say we can expect this one, but if it is existing means we will be going to the next step. The next step we are going towards that one. But if it is there, so we switch to m by n, which is represented as this. M means the number of slots, sorry, the number of keys is called as the m by n. If it is not existing, this m by n is here is represented as s by n. Okay, so I'm just writing that one too, which will give you the idea. Is m by n. This m by n is represented as s by n, which is there. So definitely we should know the two conditions while we are getting. So indirectly we can say if it is m equal to n, so in this case we can say 1 would be our answer, less than or equal to 1. So which I told you. So less than or equal to, we can say if m is equal to n. M here is s, they are represented, means the number of slot or the number of keys are considered as m, number of slots are considered as n. So in this way we have observed that whether it is within 1 or it is within 2, that we have decided now. I hope it is clearly understood to you. Next, the designing of universal hash function. Basically modulus, whenever we're doing the modulus, indirectly we are focusing on the hash function. So here they introduce a prime number p for size of a hash table. In general they said like p will be more than equivalent to m, means the number of keys, it should be more than or equivalent to the prime numbers. It is written in the book. Okay, so on other contents also, when I have searched, there are many different research papers I have gone through. As for the research paper, what they said, p is a greater than equal to m. So they have just mentioned that one. Many papers, many different contents, they have presented their own way. So here the integer encoding they have introduced, where uniquely identify the elements, like which are a small u that belongs to the universal set. Base p represents a prime number integer of r digits, means the digits present within the element x will be like x1, x2, xr. So hash function, how do we select, like how do we design the hash function for it, is for a is a set of r digits, for all r digits, with a base of prime numbers. Basically we have to select the prime numbers. Next, for each a, which is within the capital A, which is a to r, means r number of digits, where the ai, any value which you are picking, that should be greater than p. That's why I said the p value should be greater than equal to m, means the number of keys that we are picking, that should be less than or equivalent to the prime number, you can say. So I'm just writing it here as per the book. I have collected this information, that's why I've just written it. So for this, whatever the function you are exactly maintaining or redesigning, it should follow this condition, which will be lies in between the universal set, like as you are taking the value of prime number. So prime number, you can start with the p 0 to p minus 1. Based on that, you just find it out, because prime number says the slots available within this, the slots when we started, so it should be started from 0 to the p minus 1, like as we have seen, like 0 to n minus 1. So hash function family, like the HA, where A belongs to capital A, and this HA, small ha, belongs to capital H. So this is what the designing of universal. In summary, I just want to brief it, like which we have already completed. I'm just telling you, like the goal what we set earlier is, given universal U, maintain a subset S, that like S with subset of the universe. So our target is insert, delete, and lookup should be efficiently used. Like efficient in the sense, our time complexity should be at least equivalent to 1 or towards 1. Okay, so the universal hash function family, which belongs to this one, that we can design uh, using this method, and choose the prime number, which I told you, like prime number that should be in 2 into m, like the number of keys which we have, that should lies in between. But it depends on the content, as I've seen, like as I told you, like p should be greater than m. So here it says like it should also be less than 2 of m. So where m is the size of the subset. Next fact, there exists a prime in between m to 2m. Can find such prime using another randomized algorithm. You can use a randomized algorithm to find the prime in between those two. So the consequences is, like the space used is, definitely we can say, either you can use theta, which is average case, or you can say big of m also. That is correct, not an issue. But in general, we are not expecting exactly that one, so that's why we are representing that one as theta. So theta of n is our expected space complexity, but the expected the number of collisions operation is less than or equal to 1. And the complexity, our target was, as I told you, like it should be big of 1 for all these three operations, which has to be taken care of. So I hope you got the idea about the universal hashing. If there is any doubt, you please comment below. Thank you and have a good day.